On January 3rd, 2026, tracking data showed 3i Atlas shift in a way that orbital models said shouldn't last. At first glance, that sounds insignificant. But in orbital mechanics, changes this small are expected to fade quickly, not remain stable. This adjustment didn't fade. It stayed measurable across multiple observations. That matters because objects moving through deep space, especially interstellar ones, usually settle into predictable paths once external forces stop acting on them. But this one didn't, and that's where it gets strange. Because if nothing is pushing an object, its motion should smooth out over time. However, in this case, the change persisted, even when models predicted it shouldn't. That doesn't mean something extraordinary is happening, but it does mean scientists paused. And when scientists pause over a tiny number, it's usually because that number doesn't behave the way it's supposed to. To understand what changed, we need to keep this simple. To keep this 3i Atlas is moving through space on a long curved path shaped by gravity. Normally, once an object like this passes the strongest gravitational influences, its motion becomes steady. Think of throwing a ball. Once it leaves your hand, it follows a smooth arc. But imagine throwing that ball, and halfway through the air its path bends slightly. Not because of wind, not because of another hand, but for no obvious reason. That's the kind of shift scientists noticed here. The data showed a small but consistent deviation from the expected trajectory. Not a sudden jump, not a dramatic turn. Just a quiet, persistent adjustment. And that's important, because random noise in measurements usually cancels itself out. But this didn't cancel out. However, before jumping to conclusions, scientists had to ask a basic question. Is this real or just a measurement artifact? So they checked again. Different instruments, different observation windows, different tracking methods. The shift remained. That doesn't mean it's unexplained, but it does mean it's not easily dismissed. Under normal conditions, small trajectory changes happen for clear reasons. Gravity from nearby objects, outgassing if the object is releasing material, radiation pressure from sunlight. All of these can push an object slightly. But here's the issue. For an interstellar object, like 3i Atlas, those forces should weaken rapidly as it moves farther away, which means any change they cause should also weaken. But this one didn't fade the way models expected. That's where it gets strange. Imagine a car rolling uphill with the engine off. It might move a little, but it shouldn't keep going. Yet the data suggests this adjustment maintained itself longer than expected. Not dramatically, not violently, just quietly enough to be noticed. However, this doesn't break physics. It challenges assumptions. And in science, that's often more interesting, because assumptions are built on averages. And averages don't always describe rare cases perfectly. So, the question isn't, what is this? The question is, why didn't this behavior disappear? Let's separate what we know from what we're guessing. Explanation 1. Normal, natural causes. The most conservative explanation is that 3I Atlas is experiencing a subtle, ongoing force we haven't fully measured yet. For example, uneven heating. If one side of the object warms more than the other, it can release tiny amounts of material. That release can act like a gentle push. Even a very weak push, applied consistently, can cause a measurable shift. This has been observed before with other space objects, so this explanation fits within known physics. However, there's a problem. The data doesn't clearly show the usual signs of strong outgassing. No dramatic brightening, no obvious material plume. That doesn't rule it out. But it makes the explanation less clean. And that's where uncertainty enters. Explanation 2. Rare or unresolved behavior. The second possibility is that 3I Atlas has properties we don't fully understand yet. Its shape, its mass distribution, its surface composition. If the object is irregular enough, even weak forces could produce unusual motion. But here's the issue. Models that account for extreme shapes still predict that these effects should fade over time. Yet the change persisted longer than expected. That doesn't mean the models are wrong. It means they might be incomplete for rare interstellar objects. And that's not alarming, it's normal. Science often advances by finding edge cases that don't fit neatly. But it does mean this object remains unresolved, not explained. And unresolved data keeps scientists watching. So what happens now? The next step isn't speculation, it's patience. Scientists are waiting for additional tracking passes, longer observation arcs, better signal clarity. Each new data point helps determine whether this adjustment is stabilizing, fading, or evolving. If the change slowly disappears, the mystery likely resolves into a natural explanation. But if it remains measurable, or grows, that will force revisions to current models. And that's where things get interesting, because revisions don't mean something extraordinary is happening. They mean our understanding is being refined. However, until more data arrives, one question remains open. Why did this small change refuse to behave like it should? That answer isn't available yet, but it's coming. And when it does, it may quietly reshape how we think about objects traveling between stars. Subscribe to follow the next update, because in space, the smallest numbers often matter the most.